Determine if each pair of planes is parallel, perpendicular, or neither. I think that people would assume that having vectors that are parallel to a plane would be useful. That would be a useful piece of information. When you look at the vector form of the equation of a plane, it has two direction vectors in it. So for that form, that's useful. And those direction vectors can't be collinear, right? They need to in order to define the plane, they need to be not collinear. And I need 1 point as well, right? So I think even like just thinking about the vector form of the equation of a plane and thinking about how we did a lot of work with vectors, knowing vectors that are parallel to the plane, you might think of them as in the plane. The vectors don't really exist in a plane necessarily, but that would be useful bit of information, but turns out it's not actually all that useful. Okay, so think about this. So I've got two planes here. There's a few vectors parallel to that plane. What do they share in common? Nothing. Right? Those three vectors share nothing in common with each other, really. Except that they're all parallel to the plane, I suppose. What about these ones? Same thing. What about when I look at, I know you can't see, but you can kind of visualize if you think about these two. And when I take these two planes and I make them parallel, what do I notice about those vectors? They still, they have nothing in common with each other or between the two planes with each other. So all six of those vectors, there's not really much relating them. Do you agree with that? So if I had a plane and I came up with a random vector in that plane and a random vector in this plane, these are two planes, pi 1, pi 2, right? We call those, Rich said that the other day, we often use pi to talk about planes. Would it be helpful to compare those vectors to each other, a vector in this plane and a vector in that plane, to try to come up with some relationship between the properties of the planes? You see what I mean? So if I take two random vectors, one in one plane, one in another, could I examine those vectors and draw conclusions on the planes? See where I'm going with this? A little bit? Because I can determine if two vectors are parallel or perpendicular. So if I did that, would I be able to conclude something about the planes? Are you thinking about this, or are you waiting for me to tell you? What do you actually think? I think it's pretty easy to come up with. Go ahead. What do you think? That's not the question that I asked. You just gave everything away. Yeah, that's fine. It's okay. Yes, that's where we're going with this. So let me jump in here before you go on with that thought. You could come up with a lot of counter examples, like I just did, where I have two planes that are parallel, but there's nothing about these vectors that's useful. Sure, I could have two vectors that are parallel, but that's going to be hard to track down. There's going to be a lot more examples that don't work than that do work. Does that make sense? Kind of following me here? So there's a lot of counter examples of vectors parallel to the plane where they don't share any properties. So using vectors parallel to the plane, or if you think about them as in the plane, that's not going to be useful. So, let's see it. What were you saying? So this is the whole point, is the normal to a plane is more, it's not unique, but I mean, it's not unique because you can scale or multiply, right? But It's unique in that there's only one set of collinear vectors that are normal to a plane. So that I can use to tell. One thing that's interesting is if I take any of these two vectors and I take their cross product, it's going to be the same, or it's going to be scalar multiples of each other. Those are going to be collinear. All the cross products are going to come out of the page at a right angle. The cross product of these two, the cross product of these two, or the cross product of these two will all be similar in that way. So that's useful information. That's the information that we want. Okay, so that's what we're going to do is, and we kind of saw this previously, I think, but when we're working with planes, we almost always want to be thinking about the normal, kind of depending on what you're being asked, right? But we can use the normal and compare it to other normals and then draw conclusions. So what's the normal for plane 1? Who remembers this? It's easy. Sometimes it's dangerous asking easy questions. Ayla? 2, -3, 8. So it's from the coefficients of the x, the y, and the z. Wouldn't it be nasty if somebody gave you a question and the variables were out of order? It was like x, z, then y, and you didn't check carefully. I always double check when I do those kinds of things. I always think to myself, like, oh, make sure they're in the right order. Could be a typo, or it could be that you were working with it and accidentally wrote it out of order for some reason. Okay, go ahead and do N2. -6, 9, -24. Does that look right? What do you think? John? Times -3. So I can show this a couple of ways. I can do this. -6 over 2 equals 9 over -3 equals -24 over 8. It all equals -3 over 1 or -3. Very good. Like, you can think about it as a big, long proportion statement there. But what I'm actually going to say is since -3 times n1 equals n2, therefore, what does that mean? The vectors are collinear. They do happen to be pointing opposite directions. Yep. What conclusion can we draw about, like, how does this help us answer the question? The question was, determine if each pair of planes is parallel, perpendicular, or neither. Emma? Yeah. Yeah, the normals are parallel or collinear, so the planes must be parallel as well. Very good. So N1 is parallel to N2. Therefore, plane 1 is parallel to plane 2. To me, this is the important thing to state after you've come up with both normals. And I mean, that was by inspection. We just looked to see if one was a scalar multiple of the other, right? But then I stated this. If I skipped that step and went straight to this, it'd be like, what do you mean? You wrote two normals and said, therefore, they're parallel? That doesn't really make any sense. So if one is a scalar multiple of the other, then they are parallel. Does that make sense? Okay, let's try another one. We're going to do it the same way, so go ahead and get started on that once you've written it down. What's happening with this one? What do you think so far? Like what, did you write this down? Everybody got this far? And what'd you do next? Come on, folks, help me out. Solve it like the last one, right? So what do you think? And is it? Does not look like it is. Can you prove it's not? There's nothing tricky going on here. Is 2 over 6 equal to negative 3 over negative 4? No. So there's no proportionality here, right? So we're going to say n1 is not equal to some k times n2. Therefore, pi 1 is not parallel to pi 2. That's what I would start with. I would check to see if they're parallel. And they're not. Okay, what do we do next? Yep. Why the dot product? How will the dot product tell us if it's perpendicular? So if the result of the dot product is 0, remember the dot product, when the dot product is 0, two vectors are perpendicular. Good. So n1 dot n2. I got 12 plus 12 plus 24. Is that what it looks like to you? 48, which does not equal 0. Therefore, pi 1 is not perpendicular to pi 2. Are neither parallel or, whoops, perpendicular. Okay. So in the end, pretty straightforward, although I think there's sort of some good visualization, some deeper understanding there, thinking about the normals, thinking about planes in general. As I've said all along, it's really important that you spend some time visualizing this and thinking about it. But the normals are what we want to examine. I mean, that's super important. And to check if they're parallel, we can just check by inspection. To check if they're perpendicular, we're going to use the dot product. If we got that wrong on the test and use the cross product, that's really wrong. Cross product will not show us if they're perpendicular. So you can't get that mixed up. Okay? Questions before we move on? So this is interesting. Find the angle between the planes in B. What does it even mean to be an angle between planes? Because different vectors in those planes would have different angles between them. So the angle between the planes, as we are going to calculate it, is not the angle between all vectors in each of the planes, right? In fact, vectors in a plane have angles between them. So then if I have two planes that are at an angle to each other, what does that mean? So we're going to find the angle between the normals. And that's what we would call the angle between the planes. Does that make sense? Pretty straightforward. That would be, I think, intuitive. That's probably what you would guess. And we do this the same way we did previously. So if you remember, the cosine of the angle is equal to A dot B over the magnitude of A times the magnitude of B. This is a rearrangement of one form of the dot product. We never started with this as a formula. That's not something we did, but we always kind of started with the dot product formula and rearranged it, but it's the same thing, right? You could use the cross product with the dot products a little bit easier. Actually, you can't really use the cross product for this because we don't know the n necessarily, but like that is a different formula that you could rearrange sort of, but it's way better to use the dot product. Plus, we've already done half of this, okay? Because this is the same question from the last example. So n1 is 2, -3, and 8. I'm just rewriting this. And 2 is 6, -4, and 3. And we already calculated this. If we hadn't, then you would have to do it. n1 dot n2 is 48. What else do I need for this formula? The magnitude of n1 and the magnitude of n2. So cos theta equals 48 over root 77 times root 61. Try that on your calculator. I got 45.5 degrees. Rounding is a funny thing, eh? Especially like you're in grade 9. What you round to is always a big deal, and some people don't know how to round, and so they make mistakes all the time and don't really get it. And then people, what should I round to? What should I round to? Usually we round angles to the nearest degree, but like if I ever got an angle of 45 or 30 or 60 or 90, and it wasn't exact, I would include a decimal just to say, hey, it's not exactly 45. I mean, I have the rounding symbol here. I always use that anyway, but you know, I would always be careful to communicate this is not an exactly 45-degree angle or something like that, because when that happens, sometimes that's important, right? Anyway, just kind of one of those side notes of why we round. Okay, one last question. Find A if you have the equation of two planes in scalar form, 2x plus 8y minus 4z plus 1 equals 0, but look at pi 2. It's ax plus 20y minus 10z plus 9 equals 0. So find the value for A that makes these two planes parallel and that makes the two planes perpendicular. Why do you think you're asked questions like this in math class? Like you're asked questions like this through every grade of high school for sure. I don't know that there's a real life application to a question like this. Why do you think you're asked? Jason?
Make sure people understand how and why everything works.
Yeah, I think it requires a bit of a deeper understanding of what the relationships between the planes have to be in order for them to be parallel. Or in order for them to be perpendicular. So it's not check if they are, it's make them that way. Maybe you already know this, but a little secret. Making up questions that work well is hard. Like, it depends on the exact unit that you're working in. But, for teachers to do that, sometimes it's really hard to make questions work out a particular way. Make different questions work out in different ways. It requires a pretty deep understanding often. But we're going to do these the same way we were checking if they were parallel and perpendicular. So we're going to talk about the normal for sure for both of these. What do you notice about those two? Anything? It's actually not as obvious because it's not like it's not a whole number multiple. 2.5 works for both of them. So 8 times 2.5 is 20. What about 4 times 2.5? That gives me 10. Yeah, it does. And it better. What if it didn't? Then you couldn't do it, right? Think about that. If it was one number for this and a different number for that, then you can't make the two planes parallel. So I'm going to do it like this, though. 2 over a equals 8 over 20 equals negative 4 over negative 10. Or what if it was negative 4 over positive 10? Again, then just right there, you wouldn't be able to do it because it has to be the same multiplier for all three, right? If I set it up, if I can find the value by inspection, great. If I can't, you could divide, just do 20 divided by 8. Oh, that's 2.5. 10 divided by 4. Oh, that's also 2.5. Okay, this is working out. But you can also set up a little equation like this or a proportionality statement. And then I'm just going to use one of these. And I'm going to solve so I get 8a equals 2 times 20, which is 40. Divide both sides by 8, and I get a equals 5. Or 2 times 2.5 would give me the 5. So a equals 5 will make the planes parallel. And remind me what I'm going to do to make the planes perpendicular. What tool do we have that lets us check things perpendicular?
Dot product equals 0 and then we solve, right?
Yeah, dot product has to equal 0. So this is going to be n1 dot n2. And that's 2 times a plus 8 times 20 plus negative 4 times negative 10, which is 2a, and it's got to be 0. So I'm going to sub 0 in for the dot product because that's what I want the result to be. Plus 160 plus 40. Move that stuff to the other side. I get 2a equals negative 200. So a must be negative 100. And if a is negative 100, then the planes are perpendicular. Any questions? So more working with, this is from the worksheet you got last week. More just working with planes, different questions with planes. I cannot stress this enough. It's one of those things that when we're doing it together as a class, it might seem straightforward, but it's not necessarily. You got to go through this thinking yourself. You got to try some of these yourself. You got to spend some time visualizing and thinking about these relationships.